move this atom, say from this side to this side, they get they have a different hopping amplitude than when they hop from this black dot to this black dot, because the orbitals which they have to go through, they have a spin orbit split. So they have different energy position. That gives them a different hopping amplitude, which is sort of described by this term in this tight binding, in the tight binding description of the electrons of the two-dimensional layer. Now, this has been confirmed by careful, in this paper, by careful first principle calculations, and they found that in the case of, I think, thallium, the gap which is induced by these atoms, these heavy atoms that are placed on top of graphene, can be as large as 21 millielectrons, which is a sizable gap. So, yeah, these authors argue that by doing this, one could turn the graphene, which is a system that lacks of much spin orbit coupling, into effectively a system with a strong orbit coupling, which would become topological insulator. Now, another idea, which was put forward by Cazalilla and Guinea, is to use not heavy atoms, but very light atoms. And the idea is that if you, for instance, take hydrogen, when hydrogen is deposited on graphene, it will strongly bind a carbon atom. Right? It will form a chemical bond with it. And as a consequence, it will pull out this carbon atom from the graphene plane, so it will induce a local deformation. Now, local deformation in graphene, right, this deviation from planarity happens through what the chemists call sp2, sp3 hybridization, which is essentially a mixture of a different combination of s and p orbitals, right, different from the one that exists in perfectly flat graphene, which is symmetric under mirror symmetry. Now, when that happens, this admixture of s and p orbitals enhances locally the spin orbit coupling and leads to locally to another type of spin orbit coupling, which is not the same that this was discussed by Kane and Melle. It's what is called Rashba spin orbit coupling, and I will explain in a minute. And this local enhancement can lead to local spin orbit coupling, which can be of the order of, say, up to 10 millielectron, which is comparable to what you have in diamond, which is another carbon allotrope, where the bonds between the carbon atoms are not essentially sp2, not this symmetric version of the mirror symmetric version of the bonding, but this like sp3. So why is this interesting? Because recently, in an experiment in the group of Barbaros Silmas in Singapore, this idea was actually confirmed, and it was confirmed by detecting the spin Hall effect. So the idea is to take graphene, you make a device, and then you hydrogenate this device. You sort of deposit hydrogen. This is a picture of the device. It has this funny shape, which is like made of many adjacent H devices, like this one here. And the reason is that this is an ideal device to measure the spin Hall effect. So what you do here in an experiment, then you use this version, which is a simplified version of this. The reason why they have all these terminals here instead of just 4 is because they can measure also the distance, the dependence of the effect as a function of the distance along this direction. So let's use this simplified version. So what they do is they pass a current through one of the arms of this H, okay, like this one here, for instance. Now you see that this is a normal current, okay. Now, by virtue of the spin Hall effect, this normal current will generate a spin current perpendicular to it. Now, in transport theory, there is something called Dion-Sager relations, which tells you that if you have an effect, you also must have the inverse effect. So there is something called the inverse spin Hall effect, which tells you that if you pass a spin current through a material that exhibits the spin Hall effect, then you will generate an electric current perpendicular to it. So this spin current here on this section of the device leads to a charge current on this other arm of it. And therefore, you detect this charge current as an accumulation of charge on this point, which leads to a non-local voltage. Okay? So that's what these people did here. It's a standard kind of measurement for this effect. And this can be seen, as I said, as a non-local signal, non-local voltage. So if you divide this voltage by this current, by intensity here, you get a resistance, right? And this is the non-local resistance. So what you have here is in red, the result of measuring the device after it has been exposed to hydrogen, and before it's exposed to hydrogen. And what you have here is called, this dashed line is called the ohmic. These are the ohmic losses. It's the fact that, well, in general, in a device of this size, current does not go in a straight line from one point to another. So even if you apply an electric field between these two terminals here, these two leads here, some of the current is leaked and it goes to the other terminal. So, but what you can see is that in any case, this leakage right here, this is the leakage in the hydrogenated device, is much smaller than the signal that you get, the total signal. So this is clearly telling you that when you expose the device to hydrogen, you are generating a spin current. And in this paper, they also have other evidence like the existence of precession and so on and so forth. So this is an indication of, yeah.
The contact resistance is subtracted?
These are actually devices where it's quite large. So
okay.
Yeah, it's not ballistic. It's actually, so the resistance is dominated by the device, not by the contacts. And this is the dependence of the non-local resistance signal with the hydrogen coverage. Now it's important to emphasize that the coverage here is very, very small. It's at most 0.0506%. And the reason is that if you expose the device, the graphene, to much more hydrogen, then it becomes too disordered, and then the mobility of the electrons in this system deteriorates very rapidly. So then it no longer becomes useful for any application. Right? So whatever the applications I give for this. Now, in principle, this picture could be understood from the idea that you have isolated atoms, in this case hydrogen atoms, that locally induce spin orbit coupling on the graphene sheet. The only problem is that, well, we know graphene, this is an experimental fact, is not flat. This is perhaps, although it's not fully understood, related to the fact that there is a theorem in statistical mechanics that tells you that, or also in high energy, tells you that there is no long-range order in 2 dimensions. Right? And crystalline order is for example. Right? So the reason why graphene exists is because the samples are typically not infinitely large, not in the sort of what would be the thermodynamic limit, and the bonds in this graphene layer are like very, very stiff. So, but in spite of the fact that we have a stable graphene, at least on the scale of experiments, so it's even longer, much longer. This graphene cannot be perfectly flat. So there is some fluctuations which are measured in the form of ripples in this layer, and these ripples actually change the properties for the absorption of atoms. When you sort of throw some atoms on this landscape, they will prefer to see on certain places and not on others. And these places are actually the top of these hills here, these ripples. And one reason is that if you're trying to form a chemical bond, for instance, like hydrogen or fluorine gas, that's where the pi orbitals of the carbon atoms are farther apart, right, pointing in sort of divergent directions, if you want. So if you can form a chemical bond here, essentially, the electrons of the nearby atom are not going to be annoying you so much. But this is backed, actually, this kind of naive expectation is backed by calculations that have been done for a long time. For instance, it has been done for a long time that if you take a nanotube, which is nothing but one of these graphene sheets, and you roll it up, right? And you look at the absorption energy or binding energy of, say, hydrogen or aluminum atoms, and this roll carbon sheet, then this absorption energy is much higher. This binding energy, sorry, not the absorption energy. The binding energy is much higher for a smaller radius of the nanotube and for larger radius. So it goes, this is essentially a measurement of the curvature. The curvature is much higher here than here. So it's telling you that the more curved, the easier for the atoms to stick, the stronger the bonds. So they will form bonds around the tops of the hills and not so much on the valleys, right? So that reflects essentially a tendency to cluster. So when you deposit atoms on the graphene sheet, they are going to cluster, and that must be important. And actually, my colleague Paul Chu in NTHU has actually beautiful pictures, not of hydrogen, but of copper, which is which appears on a certain process which is used to manufacture graphene these days, and this copper actually clusters and can form clusters of sizes up to 15 nanometers, which are quite big. Right? People have even done experiments where they have measured the spin transport, like the spin lifetime, on graphene after depositing clusters of atoms, like in this case, an experiment done by Kawakami in Riverside, California, where they deposited gold clusters. Now, what we would like to ask then is, what is the effect of these clusters on the spin Hall effect in graphene? And coming back to my first question here, right? My earlier question is, we would like to study the scattering of electrons, the skew scattering mechanism, with these rather big clusters deposited on graphene. And we can imagine that essentially these clusters can be described in a continuum limit description by a certain potential which contains two parts. One which is nothing but a scalar potential that we add to this two-dimensional Dirac equation, and another part which is describing the spin-orbit coupling, which is induced by these atoms in the cluster, right? Like the one that is induced by hydrogen, which distorts locally the lattice of graphene, or the one that might come from the fact that we are depositing heavy atoms like gold, which also induce spin-orbit coupling. Now, in a minimal model, one can write down two types of spin-orbit coupling. This one I have already shown before is the one that was discussed by Kane and Melle. Exists in perfectly flat graphene. It's invariant under the mirror symmetry of about the plane of the layer. But because you have all these things that perturb the mirror symmetry, that break the mirror symmetry, you can also induce another type of coupling locally, spin-orbit coupling, which is known as Rashba, okay, after the name of his discoverer. So how are we going to study the skew scattering in this this model. What we are going to do is we're going to compute the T matrix, which in the language of wave functions means that we have to solve the partial wave problem. Okay, and this, in the continuum limit, in using the Dirac equation, is just a relatively simple exercise of solving two-dimensional Dirac equation in the presence of these potentials. And we can assume, for instance, like a circular shape for the size of the cluster. Okay. Now, before I go into detail, the results of the calculations, I would like to do something very simple, which is use the symmetries. Okay, that's something that binary physicists, for instance, use a lot when they study scattering.